Alright, so the purpose of this video is just to show you the relationship between basic feasible solutions and vertices on the feasible set. And so I just wanted to do a specific example where we look at that. And so you'll notice that the example laid out here is the example from earlier, slightly changed. So for one change is I don't have x3 for some reason, I put that in. And the other change is that x2 is now going to be strictly positive. Okay, and so let's go ahead and put that into our standard form. Oops. And so for standard form, we just have to introduce our three variables, slack, XS, and slack. We create our matrix and our equation system of equations. So this is A, whoops, I keep hitting the wrong button here. A times X equals B. Okay, and now we look at the matrix A, and remember how to get a basic feasible solution. We select several variables to be 0 and then solve for the others. When I say several, I mean if this matrix here now is 3 by, is this 3 by 5? Then I'm always going to select two variables that will be 0, and then I'm going to solve for the other variables. And so just as an example, suppose I want the first three variables, x1, x2, and s1, to be the basic variables. Then we looked at this a little bit before. Our solution then is 3, 4, 3. And because the solution has all greater than or equal to 0 values, then we're going to say that this solution is feasible. And so the objective function is just -7. Okay. Now on the other hand, if I choose 1, 2, 4 as the basic variables, that means variable 3 and 5 are 0, and that gives me 2, 5, 3 as the solution. Okay, that is a feasible solution, and the objective function you could check is 14. And then similarly, 1, 3, 3 is given by selecting basic variables 1, 2, and 5. Now remember, if I wanted to actually compute this number 9, value -9, I would put these variables into the value z. Whoops, into the value z. And so in this case, right, I've got 3 times 1 plus 2 times 3 is 6. Oops. Did I do that incorrectly? Yes, it's 3 times the first one minus 4 times the second. So it's, what is that? 3 minus 12 gives me the -9. Good. Okay, so you can kind of see how to get that. Very good. Okay. So those are the three basic variables we started with. Now these were just presented in random order. Nothing special about that. But here we talked about this in class, you could do more. So for example, if I'm solving for 1, 3, and 4, variables 1, 3, and 4, given that variables 2 and 5 are equal to 0, then I get 7, 15, and -12 as my three answers for the solution. And now because this has a negative value in it, it is not a feasible solution. Okay. Similarly, if I'm using variables 1, 3, and 5, I would solve my system, and that means 2 and 4 are equal to 0, right? 2 and 4 are equal to 0. And then I would end up with this -5, -9, 12. That corresponds to a non-basic feasible solution, or sorry, non-feasible solution, because it's negative values. Good, and so on. And so I will include all of these here, and you can check these for yourself at your leisure, but these are all turn out to be non-feasible. Okay, now before we leave this problem, I want to go back to this set, and I want to take a look at it, and I want to see what is the relationship between the graph of this set, the graph of S, and these solutions that are basic, or the basic solutions that are feasible. Okay, so to start that, we can just take a look, and I hope this is a clear image here, but this is our feasible set. Feasible set S. Okay, and so just to double check, can you see which lines are which? Oops. Let's see if I can get you down here. So in this case, the first line is minus 2x plus x2 less than or equal to 1. And so that would mean that y2 would be, well, you could think of it as slope of 2 and an intercept of 1, right? Do we have a line here with slope 2, intercept 1? Yep, right here. And so that's the first line, and so on. You could read off the rest. Good. All right. We'll continue up here for a sec. So in this first feasible solution here, we're just repeating ourselves over on the side here. x1 and x2 is given by our basic solutions here. And so from this, you can read off what the point is looking like in the original feasible set, right? So this is, again, the original set. And if we go to the point that's listed there, 3, 4, we end up at this point A. Okay. Now we said that this was a BFS, right? So that corner point corresponds to a BFS. Now, similarly, we could do the same thing for the next one. Or I guess maybe we'll take a look at something that's not. For example, here we have 0, 7, and then if we solve for the other variable, we had S1 is minus 6, E2 is 9, and S3 is 0. And so from these, you can tell where your what point this corresponds to in the plane. That corresponds to the point 0, 7. And if we look here at the point 0, 7, we're way up here. Right? Is this on your feasible set? No, not feasible. Right? So what I'm getting at is when we're talking about basic solutions are basically taking the right number of constraints in order to get a square system, and then just solving for your variables, and then everything else is set to 0. Right? So in the set of in the plane here, we're grabbing these constraints in pairs, and we're trying to solve. But just because we're grabbing the constraints in pairs doesn't mean that their intersection necessarily results in a feasible set. Okay. And so here's another example. Here's the point down here. I guess let's see. So in this case, we had 1, negative 3, 6 as our solution. So that's 1, negative 3, and 6. And then we found that x1 is equal to 0. Shouldn't s1 be equal to 0 too? We should have 2 zeros in that list. So let's double check that really quick. Here's my s1. What was x2 equal to? x2 is equal to 1. Yes. If x2 is equal to 1, then s1 must be equal to 0, right? Okay, so then this point corresponds to the point 0, 1. Do you think that's a feasible set? Nope. It's down here. Okay, so where are the feasible sets? Where are these points? These points line up exactly with, is that the end? Ooh, these points line up exactly with the corner points of your polygon. Good. So that's kind of an amazing thing, right? Maybe you're thinking that. Yes. So what we haven't talked about is how to find the relationship between like neighboring BFS. So what we're going to be doing in the algorithm that we're looking at is we're going to be taking a feasible set, and we're going to start on a corner, and we're just going to start stepping through the corners one at a time until we find the optimum. That is basically our algorithm. Of course, there's a lot of stuff. You can see that there's a lot of machinery here building up to prove that, but that's basically what it is. Good. Okay, so in the next video, we're going to talk about one last way of representing a point in the feasible set, and that's the representation theorem. Before I do that, in the next video, I guess we're going to be talking about convex sets generally again and directions of unboundedness. So I'll see you then.